Welcome to another session of this course on line commutated and PWM rectifiers. And today we will talk primarily about the per unit DQ modeling of the VSC and subsequently how we can design controllers using Bode plots. Okay, so this is how this is the content of today, and we are roughly in the sixth week, fifth or sixth week of this course, and we are going to talk about this designing of controllers using Bode plots. And probably in the next lecture session I will go through how we can make this thing in MATLAB. I'll show you how we can do it in simulation, and probably a little bit of hardware details. Now so in today's lecture we will talk more about the per unit model of the grid connected VSC and the controller design using the Bode plot. So at first let us recall the model of the VSC that we had developed in S domain. Okay, and here you can see the equations that we have derived, the D and Q axis equations. So there was these converter D axis voltage and converter Q axis voltage, and this was interacting with the grid voltage, the D axis, and we have aligned our D axis with the grid voltage space vector. So the Q axis component of the grid voltage space vector is 0, and when they align, so then the current starts to flow, and which is dictated by this R plus LS. But as you might have, we have discussed it in details, there is also these cross coupling terms that come, right? And this is the overall plant model. Okay, so this is the VSC model that we had seen. So now what we'll do is we will so as we have said that the converter can be represented as a block or the plant in the control diagram. So this whole this set of blocks and here can be all transferred or becomes the small signal DQ model of the VSC. It becomes the plant with having this as the input and this as the output. Okay, so we basically we are actually controlling the D axis current and Q axis current of which is going out of the VSC, and which is responsible for controlling the active and reactive power independent of each other. Okay, so as I told you previously, therefore the voltage source converter behaves something like a current controlled voltage source converter that we must maintain, because this is therefore the voltage source converter. As you can see here, we are controlling the current, okay, IGD and IGQ. So basically we are controlling, so this is becoming a current controlled voltage source converter, and this is precisely the reason why it is also called the vector control or grid oriented vector control, because like in a machine, we are also in a vector control of machine, we also control the currents. For example, we control the ISQ and ISD, the torque producing component and the flux producing component of the current. Here we are controlling the active and reactive power components of the grid current. So let us get to the per unit model, and in the per unit model what we see is, and it's very simple actually to derive the per unit model. The question, one of the question that comes up is why we are developing the per unit model. There are several reasons for this. One of the most important reason for having a per unit model is that you can when you develop a model based on a per unit, you can actually scale it up or scale it down for different rated systems. For example, suppose you develop a controller inside a DSP for a certain voltage source converter rating. Okay, for example, this is a 400 volt 10 kilowatt. Now after some time you may need to develop a 400 volt 50 kilowatt converter. If you have a model which is in per unit, then this transition from 10 kilowatt to 50 kilowatt becomes very easy, because you will just change the base quantities, and you can because the controller parameters are all designed on the per unit values, then the design becomes the process of transferring from 10 kilowatt to 50 kilowatt, this transition becomes very easy. In fact, it's a few lines of codes where you just change the values. So this thing I will show you when I am showing the MATLAB simulation. So this is one of the reasons why we go for the per unit model. Okay, and so when you go from this 10 kilowatt to 50 kilowatt, the transition becomes very easy. Okay, so having a per unit model, so I will show you later in the during the MATLAB simulation. When I will show you the MATLAB simulation, then I will change the converter rating, and you can easily see how the controller tuning is automatically taken care of. So this is one of the reasons for having a per unit system. And the other thing that also is important when you use a per unit system is that you can actually understand that what are the limits or what are the maximum and minimum values of different variables. Okay, what is the contribution of certain parameter, certain expressions in the whole converter system. So how much is the contribution of the cross coupling term? Okay, because per unit system means it goes between +1 and -1, so you will be able to understand what are the contributions of the different expressions in it. And another very important reason why a per unit system works very nicely is that in per unit system all your variables are between +1 and -1. So for example, your reference will be always between +1 and -1. Your Kp, Ki values will be always between, the output of the controller will be always between +1 and -1. Okay, so it becomes very easy during your debugging process to know to actually put a saturated limit on the PI controllers, for example. Okay, suppose you put a saturated limit of +1 and -1, it will be valid throughout for all the blocks. Okay, this is something which is very important. In fact, when you develop a non per unit model, a general model, then you always don't know what are the maximum and minimum values for the saturated block that you have to use. Okay, what is the maximum capacity of the voltage source converter? Okay, how much it will during transient condition, how much will it maximum provide? But in a per unit model, you always know that the maximum that the voltage source converter can provide is 1 per unit. Okay, whether it is a voltage, whether it is a power, or whether it is a current. So you have already know that these are my limitations, and so when you are developing that simulation or even in the hardware, you know that my maximum and minimum values are this only. So therefore we have seen over years that having a per unit model actually helps a lot. So how do we develop this per unit model? So it is very easy actually. So this equation which we got in the previous slide here, Vconf D and this Vconf Q, what we can do is we can actually divide by the base quantities, right? So for example, Vconf D is now divided by V base, and similarly you can see V base is nothing but Z base into I base and so I divide R by Z base and IGD by I base. Okay, so if I do this, you can see here V con D now becomes V con D per unit. Okay, and R by Z base becomes R per unit, and this becomes IGD per unit, like that. Okay, similarly you can have this one here again like this, and LS by Z base will become L per unit times S per unit. Okay, this is important, S per unit, which means now we are the frequency is also in per unit. Okay, so when you draw the Bode plots, your x-axis will be in per unit, the omega plot is, the omega axis will be in per unit. And similarly then you can follow it. For example, V grid, this will become like this, and this will become like this here. Okay, the per unit equation seems very similar to the original equation. So we can simplify and write it like this, this way in the S domain, and these are the expressions for them. And in a similar way we can also draw write down the converter q-axis converter equations, which are something like this. All quantities are now in per unit, right? So we can now develop the model of this in a diagrammatic way, or in the form of a control block diagrams. And then this block diagram, which was there earlier, now is getting modified to a per unit block diagram, which is shown here. Okay, all quantities here will become in per unit, right? You can see here these are the omega per unit and R per unit, L per unit, like that. Okay, so exactly in the similar fashion, the converter will now be represented as a per unit plant in the control diagram. Okay, where all values will be in per unit. So you can see here we have developed a small signal per unit DQ model of the VSC. Okay, where these quantities are in per unit. Okay, these are in per unit, and these are also in per unit. Okay, so IGD and IGQ will be going from, say, -1 to +1, right? So now we are no longer will tell that IGD is 100 amperes or 200 amperes. We will say that IGD or IGQ, IGD, if it is, suppose we take a convention that it is flowing from the converter towards the grid, we will say that corresponding to 100 ampere, 1 per unit of IGD is flowing. And if the current is flowing from grid to the converter, then we may say IGD equal to -1 per unit, if, say, our base current is 100 ampere. So therefore and it is always so therefore it is very easy for us to actually understand that how much percent of our rated quantities are actually flowing in the system at any point of time, right? So yeah, so this is like this. Now this original diagram now will be changed to include a per unit model. Okay, now here one of the things is that the feedback gain will now be changed to 1. Okay, here you can see the gain which is coming from that output. Okay, this gain here, this gain is coming to the input with a gain of 1. Okay, this is the speciality of a per unit system. All other quantities you can see here, these are all shown as previously, and here the converter voltage gain has been this is the DC link, this is corresponding to the DC link of the converter, and this has been introduced, okay, here, because but this is also in per unit, so the DC link voltage is also in per unit. I'll show this one how this is developed. Okay, so this is the overall model here this IGD star and IGQ per unit quantities have been given. Okay. Now one question that is sometimes asked is, how do we get the unity gain feedback system? Here we have said unity gain feedback system, right? So how do we get an unity feedback system is that in the experimental implementation, suppose we use a microcontroller. Okay, so you can see here when you have, this is the real system. Okay, this is the voltage source converter, this is the grid here, right? And there we actually, when you suppose you are sensing these grid currents, you have a sensor gain, but then after the sensor gain you take it inside the microcontroller. Okay, so suppose corresponding to 100 ampere, the sensor gain after conversion, okay, gives you a value of say 1, not 1, maybe 2 or 3, something like that. Okay, here you have to be a little bit careful, because the sensors after doing some analog circuit processing, the sensor usually gives a voltage output. Okay, that is how we actually develop the sensors. So it may not be actually giving a current. Okay, so the ADC of these microcontrollers sends a voltage generally between like 0 to 3 volt corresponding to the current which is flowing. Okay, so for example, if the full 1 per unit current is flowing, the ADC may sense a 3 volt. Okay, and if 0 is flowing, then the ADC may sense a 0 volt, or sometimes it also is DC shifted, so it becomes the 0 means 1.5 volt, because it has to. So these are some details. What I want to say here is that you can make a gain inside the microcontroller. So after you sense the voltage inside the microcontroller, you can always insert a gain, and that gain ensures that all these feedback voltage and current are in per unit values. Okay, this can be done easily inside the microcontroller. Okay, so that ensures that H equal to 1 can be obtained. Okay, and those per unit after that gain, these Pref and Qref are given in per unit inside the microcontroller logic. Okay, because inside the microcontroller the PI controller is running. Okay, it's a set of codes which is developed using difference equations. So a set of codes are running. The input to those codes, if you give like Pref and Qref to this set of codes, it will be again between 0 and 1. Okay, for example, if you use a 16-bit system, then you will give 0 and 1, something like FF or 0, when in hex you give the values in hex, right? So then you can give that, or sometimes people use other types of formats, 4.12 format or some other things are given. But anyway, so those are details. But what I want to say here is that Pref and Qref can be given in per unit, and the feedback quantities, the gain of this feedback can be 1. Okay, and then you have a VA star, VB star and VC star, where you will generate a reference out of that controller, which is again between +1 and -1 always. Okay, because your system is in per unit. And so then that you will compare with a triangle, which is again between +1 and -1, and will generate the PWM pulses, goes to the gate driver and ultimately to the VSC. Okay, so with the gain inside the microcontroller, we can make a unity gain feedback system. This has some advantages. I will show you sometime later. So now inside the microcontroller, as I told you, we have already added the feed forward term, and with that we have actually cancelled the effect of the cross coupling term. And so the resultant resultant diagram, okay, looks like something like this. Okay, here you can see IGD star, IGQ star, and there is no cross coupling term, and there is the PI regulator here, and here is the R plus LS. This was the plant, okay, coming from the filter. Okay, this also we have seen previously, but now we are just using the per unit values. So then we can quickly find out what is the transfer function of this system. In fact, as we can immediately see, that this is a second order transfer function. Okay, and so you can write this as like this way, where GS is something like this and GCS is the compensator or the regulator. It is that Kp plus Ki by S, and therefore we can use this in this expression. Sometimes we use this GS into GCS is called the loop gain. Okay, I will explain this loop gain in a few minutes time. Okay, what is this loop gain and how this is important? Okay, what is loop gain is basically, it means the gain of the loop, which means what is gain of the loop? So you have this is the here is your GCS. Okay, so this is GS and here is your GCS, right? And of course HS is equal to 1, so the loop gain is equal to the gain of the loop, which means GS into GCS into HS, right? Since HS equal to 1 here, so this becomes equal to GS into GCS, right? Okay, so basically we are traveling the loop and finding out what is the gain, right? So this is what we said. So then this is the transfer function, and here you can see that here we can see that the IGD, the transfer function has it's typically a second order system. You can see here, this is the S square, and you know what is this 2 zeta omega ns, that function, that term comes here, and then you have this omega n square, this term comes here, right? So we can we know that how this is what I have written it here, and we can immediately depending on how much is what type of performance we would like, for example, how much is the settling time, how much is the overshoot, and these are all can be controlled by the by analyzing this second order transfer function, which is very well recorded and given in textbooks of control system. And these are the corresponding Ki and Kp values which can be used. However, we will not stop here. So this is how we can do the tuning of this thing. So the tuning of the regulators, Ki, Kp values. But we will not stop here. Actually, we will go for a Bode plot based design. Okay, and the Bode plot based design or the Bode plot based controller tuning is a much more intuitive way, and it is very easy to understand because it is a diagrammatic way. Okay, it comes with these graphs and diagrams and figures. It is always easier to understand a concept through figures or graphs. Okay, and same it is with Bode plot. Rather than with equations. Okay, it is easier to understand. So we will see how this Bode plot, using the Bode plot, we will come to the same conclusion, and we will be able to design the this one, the controller tuning. So before we start with this Bode plot, okay, let me just quickly recap a few things which are very well known, but I just want to have a little bit of recap. Okay, from the Bode plot, I will just quickly say what is the single pole response and what is the single zero response. So for example, if you have this kind of a circuit, okay, like this is a low pass filter, this is the V0 and this is the V in, right, and this is the RC, right? So here the gain of this system is something like V0S by V in S, which is nothing but 1 by SC divided by R plus 1 by SC, and we can write it as something like this, which again can be written as something like this, right? So this this is we know this one, right? So this is typically a single pole. Okay, so the GS is equal to we can write as 1 by omega 0, where omega 0 equal to 1 by RC. This is the normalized form. Okay, in fact this is J omega. So this is the normalized form of the transfer function. Okay, right? So therefore with this, so there is a single pole, and we can always draw the Bode plot. So if you can see here the mod G, and how will it look like? This mod G, it will look like a gain and then a minus 20 dB. So this is the asymptotic Bode plot. So here you will have a minus 20 dB per decade slope, and this is omega 0, and this gain here will be 1. So this will be equal to 0 dB. Okay, so this means the 0 dB I have started a little bit higher from that line, x-axis line. Okay, so this is how it will look like. So in many cases, remember that we use asymptotic Bode plot. This is called asymptotic Bode plot. Okay, this is very useful as a design engineer. The actual Bode plot, of course, is not like this. The actual Bode plot is something like this here. Okay, because at omega equal to omega 0, you can see at omega equal to omega 0, the gain will be equal to 1 by 1 plus J1, so which will be 1 by root 2, right? So this is 0.707, and 20 log 0.707 is nothing but minus 3 dB. So this point will be therefore minus 3. Okay, this will be not like that, so it will go down by 3 dB, but that is not important. Actually, this asymptotic Bode plot, as a designer, which what we are using here as a designer, is asymptotic Bode plot is very easy, because you can know exactly where is the pole, right, at omega equal to omega 0. Another important thing that we also understand is this statement here, minus 20 dB per decade. What does this mean? It means that the gain is falling by 10 times when I move on the x-axis by 10 times. Okay, so which means that if you move on the x-axis, so this is your omega axis, if you increase your frequency by 10 times, your gain will also fall by 10 times, right? Why 10 times? Because you see 20 log 10 is nothing but 20 dB, and 20 log 10 to the power minus 1 is minus 20. So minus 20 dB, and when we are saying decade, the word decade means you are moving 10 times on the x-axis, on the omega axis, and your gain is also falling by 10 times, right? So this is what is a single pole response, minus 20 dB per decade. That statement means when you have two poles, then of course you will change this one, and then you will probably use suppose you have 40 dB per decade. What does this mean, 40 dB per decade? It implies that you are moving 10 times on the x-axis, you are moving 10 times on the omega axis, and you are falling 100 times on the y-axis, right? So that is what is minus 40 dB, because minus 40 means this is 20 log 10 to the power minus 2. Okay, so you move on the x-axis by 10 times, so your delta x is 10 times and your delta y is actually 100 times. Okay, you're falling, so the minus comes because your is 0.01, 1 by 100. Okay, right, like that. Okay, so that means you are falling very fast. Okay, and that is why when you have a double pole, then your response will become like this and it will become faster. You are going to fall very fast. Even Bode is like minus 60 dB. Okay, when you go to minus 60 dB, that means you are falling very, very fast. Your gain is falling very, very fast. Move 10 times on the x-axis, you are 1000 times your gain is falling. Okay, so this is the physical interpretation of what these poles and of course will single pole, double pole, triple pole will do, right? So this is what the Bode plot means. In a similar way, you can also draw the angle plot or the phase plot of this one. And how will it look like? So you can see from this equation here is that angle of GS, right? Angle of GS will be angle of this 1 by 1 plus j omega by omega 0 here, right? So what is the angle of this one? So you can just write this 1 minus j omega by omega 0 by root over of 1 plus omega by omega 0 square, right? And this angle is what we are interested now. Okay, the denominator has 0 degree angle. So therefore this you can see easily that at omega equal to 0, right, at omega equal to 0 the angle is 0 degree, so it will start at 0 degree, right, and then at this angle this is asymptotic plot, this will go to minus 90 degree. Okay, asymptotically the angle will go from 0 to minus 90 degree. Of course, the actual implementation in the actual plot you will see something like this. Okay, the angle will go something like this, where this is omega 0 by 10 and here it is 10 times omega 0. Okay, roughly. So this angle is something like this. Okay, so it will go like this, right? So yeah, so this is the plot. So you can see here we have drawn the gain plot and the phase plot for a pole. Okay, if you have a single pole, this is the Bode plot. In a similar way, you can also draw the the single zero response. So how does the zero look like? So GS will be equal to 1 plus S by omega 0, right? This is the plot, this is the expression if you have a single zero, right? And and the zero is at S equal to minus omega 0. So therefore you can similarly plot the the magnitude plot as well as the angle plot. Okay, and how will it look like? It will look like this. Okay, again asymptotic plot, and here the angle will also go like this, 0 degree to 90 degree, and this value is omega 0. Okay, of course at omega equal to 0 the gain of this is 0 dB, so this line is 0 dB here. Fine. So actual plot again will be something like this, with this is like 10 and this is 10 times omega 0, right? So this is how the zero response comes, and then you can have that in the total plot you can have a combination of poles and zeros. For example, if you have a pole at origin, this one, so this typically, so this is the omega. So if you have a pole at origin, it will typically look like this, right? it is falling at minus 20 dB and having an infinite gain at, and then you have a 0 coming. So this is one pole, then a 0 comes here, okay, then a 0 comes here, and then you can have another pole. This is another pole coming, so this pole is coming here, and then it goes like this, and then another pole comes, and then it goes like this. So here it is, this is minus 20 dB per decade, okay, and then this will be minus 40 dB per decade, like that, okay. This is the so yeah, so another pole comes here. So this way the entire plot looks like, okay, when you have multiple zeros and poles in the whole system, right? So with this is just a recap for you, and you can then we can come back to our lecture, and we will see what is this Bode plot and how we can use this Bode plot for the designing of the or the tuning of the regular controller parameters. So here let us take a few numerical values, okay, because otherwise drawing the Bode plot will become very difficult, right? So suppose you have a you want to have design a 50 kVA 400 volt 50 hertz grid connected VSC, right? So let us first make the per unit calculations, right? So you have S equal to 50 kVA and V grid is 400 volt, right? And then you are defining V base as the peak of the phase voltage. You can see here, this is peak of phase voltage. So V grid by √3 into √2, okay. So the peak of the phase voltage will therefore become 326 volt. In a similar way, I base will be equal to how much? I base will be S by √3 V grid into √2, okay. Basically S I base is this is how we are defining, means S divided by the phase voltage, and then we do it like this way. So this I base is coming out to be 102.06, okay. So now V base into I base is 2 by 3 S base. This will come if you take this way the calculation, right? Now what is Z base? Z base is V base by I base, right? And therefore Z base is 3.2 ohms, right? And L base is 10.2 millihenry, because L base is equal to omega base into L base is equal to Z base, right? And omega base is equal to 2 pi into 50, okay. So L base will be obtained, and then you have the Z filtered, which is 0.04 Z base. So we have taken the filtered inductance to be 4% in this example. Usually the filtered inductance values varies from like 4 to 8 to 9%, 4% to 8 to 9%, something like that. Normally this is the what is the filtered value usually lies. We have taken the minimum value for the size constraints, and we have taken at 4%, and so therefore this is 0.128 ohm, and hence you can see what is L filtered. Z filtered by 2 pi into 50, which is 0.41 millihenry, and therefore L filtered per unit will be 0.04 per unit, okay. So all quantities you can see here, the filtered inductance, the currents, the voltages, all are now getting written in per unit, okay. And suppose I take a coil with Q factor of 30, and so the R filter will be 4.4 milliohm, and hence R filter per unit will be 0.0014 per unit, okay. and VDC is taken as 600 volt, which is 1.84 per unit. The switching frequency for this initial design, we have taken it to be 20 kilohertz, which is nothing but 400 into 5, which is equal to almost like 400 per unit, right? So the filter can be designed in several other ways. Actually, there is also one more design strategy where we find out what is the peak-to-peak ripple in the filter. So if you take it, the peak-to-peak ripple as 5 ampere, about 5% of that normal current, okay, then filter you can also design like this way, okay, taking this 5% as the ripple, and this equation comes from the hysteresis loop that we use, and from the switching of the filter. So this we have not derived, but this is another way of designing filters with a 0.42 millihenry. Okay, this will come. So here this V peak by this we have not discussed. So this is another way of designing the filter value. Okay. Now now when you go into the, so this is what we have now seen about the values that we are going to work with as part of the Bode plot. Now the question is, when we are moving into the Bode plot, there are certain things as a general guideline. Okay, what do we expect from the controller performance? Okay, when you design these controllers, you have to specify certain performance criteria. Okay, what are the important criteria for a voltage source converter? Okay, important criteria are steady state error. Okay, how much will be the steady state error, how much is the settling time, and how much is the transient overshoot. Okay, so these three are the most important. These three are the most important controller parameter or requirement specification that this compensator or GCS has to satisfy. Okay, so these are the three things which we will concentrate upon. Now another important concept, so I'll come back to the previous slide, but the other important concept that I was just trying to tell you a few slides back is what we known as loop gain. As I told you, loop gain is nothing but GS, GCS, HS. So you can see here, as I move here, this is the loop gain, right? Now often this feedback gain is taken as HS equal to 1. As I told you previously in one of the slides, we would like to make that HS equal to 1, and then the loop gain becomes TS equal to GS into GCS. Now why is the loop gain an important parameter? The loop gain is important because by observing the frequency response of the loop gain, we can actually predict the closed loop performance. This is very much beneficial. Okay, because all the time if you start closing the loop and getting the transfer function, it will become a complicated expression. And with the loop gain, which is like an open loop gain, you can see here we are just seeing GCS, GS and HS. If HS equal to 1, then we are just multiplying TS equal to GS into GCS, and we are going to plot only this TS equal to GS into GCS. By observing that plot, which is basically the open loop frequency response, by observing that frequency response, we will be able to predict the closed loop performance. Okay, so and in many power electronic systems, we actually go with this method of analyzing the closed loop performance by analyzing the frequency response of TS or the loop gain. Okay, this is very useful. We will see that one. Now, what do we expect from the loop gain? Okay, the loop gain. So now we are plotting the loop gain. Generally, how the loop gain looks like is that something like this. You can see here there is a trend, and the trend is that the loop gain is generally starts from a high value and falls like this way. As you can see here, both these trends are observed here. Okay, so this is the mod t, and here is the omega. The general trend is that it starts from a high value and it falls. Okay, it crosses this 0 dB line at omega cross, right? Okay, in between you can have poles and zeros, like you can see here, this has this pole and then 0 and then another pole, or you can have one pole, double pole, and then another 0, like that. Okay, so these are in between this whole omega axis there are modifications, but the overall trend, this is the overall trend. Okay, overall trend is that the loop gain has a very high value close to DC. Okay, so this is like close to DC, this side is DC, omega equal to 0, and this side is high omega, which corresponds to switching frequency, right? So we see that at omega equal to omega cross, of course the mod t will be equal to 1, because that is the 0 dB axis. But at omega less than, much less than omega cross, mod t is very high, and at omega much more than omega cross, very high, mod t is less than 1. So this is the pattern. Okay, and this is something which is which we try to maintain in all power electronic system based controllers. For the controllers of the power electronic system, we always try to maintain this one. What is the reason? We start from a high value at DC and fall with omega. What is the reason? Is that, suppose you take a example, this IGD by IGD star. Okay, IGD by IGD star, which is this GS GCS by HS, and you can write it in this way. Okay, you can write it here itself, that IGD hat by IGD star, and that will be equal to GS into right. So you can, because you can write it like this, GS GS and 1 plus GS GCS and HS, and so this will be equal to 1 by HS into TS by 1 plus TS. Okay, this is what we have written here. Okay, 1 by HS into TS by 1 plus TS, right? So here you can see, suppose HS equal to 1. Okay, so now the question is, as I told you, if the magnitude of the loop gain is very large at the operating frequency, then what will happen? This will be almost equal to TS by TS, right? Your magnitude of TS is very large as compared to 1. This will be equal to 1 by HS, right? And since I have taken HS equal to 1, this value will become equal to 1, right? So therefore, this is what we want. Actually, we want this current, the output, this current here, to closely follow the reference with a gain of 1. This is my reference here. So these two must follow each other very closely with a gain of 1. So suppose our entire system, okay, is operating in this frequency range. So our all the variables have perturbations which are very close to DC, okay, which are have very small, slowly varying quantities. At this area, in this area, you can see that the loop gain is very large, right? And because the loop gain is very large, I can get easily a gain of 1. This is precisely the reason you can see now, understand or appreciate that in DQ control, all control variables are in DC. Remember, in DQ control, okay, we deliberately did something. We had initially some AC quantities, right? Three-phase AC quantities. We converted through Clark's transformation to a two-phase quantity, AC. From the Clark's transformation, we use Park's transformation so that all my quantities became DC. And now I can appreciate why I did that and why I am developing my controllers in that. Because close to DC, you can see here, close to DC, the loop gain is very large, and that ensures easily that IGD by IGD star is equal to 1. Okay, and that is very useful because then the transfer function is independent of any variation in the plant parameters, because the loop gain is so high, right? So if you have a problem with GS, if you have a problem, you have a change or something, the R and L is changing over time, the GS is changing, but GCS into GS, that loop gain is so high that the impact of GCS doesn't matter. So this is now, therefore, in DQ control, we had deliberately taken the whole system in DC, and then we ensured that at that close to DC, or in this region, which I have shown here, in this region, the loop gain is very, very high, and therefore I can accurately track the reference. So IGD star, I give some IGD star, and the actual IGD is flowing with a gain of 1. There is also one more advantage of having a high loop gain, and that is coming because of disturbance rejection. Suppose you have a disturbance in this system, you can give this as the disturbance, and this is the transfer function corresponding to that disturbance, and this gets introduced into the system, right? So therefore you can find out what is the impact on the output because of the disturbance here through this transfer function. What is the impact? Okay, what is the impact on IGD because of V disturbance? Then you can find out this is the forward gain G dist, and divided by the loop gain, which is 1 by Ts, and clearly you can see that this is equal to G dist by Ts. And if Ts is very large, okay, this denominator is very, very large, what will happen? This value will almost have negligible impact. Okay, so the impact of the disturbance on IGD will be nominal or very small, okay, because the loop gain is very high. Okay, so this is another advantage of having a high loop gain. Okay, another point is, as I told you, so we understand that at this area we get high loop gain. Okay, so and I explained what is the benefit of this. But what happens at high frequency? At high frequencies, we would like to have a low loop gain. Okay, we want delta t to be much, much less than 1. Okay, that is why you can understand the slope is going like this. Okay, and why do we want to have that, right? Because so if the value of the loop gain is very, very small at high values, then IGD by IGD star will be equal to this expression and will be equal to this one roughly, right? And it's much, much less than 1. So this will be equal to 0, almost 0. So therefore, because what happens at high frequency? At high frequency, the switching frequency harmonics exist. As I told you in long back, when you have this voltage source converter and you have a sine PWM, then you have the fundamental here and switching frequency harmonics. They have this places, right, FC. So at high frequency, we don't want this to go into our controller. Okay, basically the controller should have very low gain for this switching frequency harmonic components. Okay, so we do not want them to propagate into the system. So at high frequency, therefore we see that we have already got or made sure that the loop gain is very, very small, right? So therefore our aim has always been something like this, that the loop gain should go like this, right? This is the TS. Okay, very small gain at this one. Okay, small gain here and a large gain here. Of course, there are in between poles and zeros, so you will change the bandwidth. The bandwidth will come here, so you will modify it here and change it up, down, like that. But this is essentially what is doing the two extremes. We have a large gain on one side and we have a small gain on the other side. So basically the loop gain should have poles to reject the switching frequency harmonics components at the other side. So we have now understood what is this loop gain and what will be the strategy. Now let us come back to the question that I put some time back, is that what are the general requirements for designing the compensator? There were three things. So if you go back here, the general requirement were how much is the steady state error, what is the settling time, and what is the transient overshoot. These three were the important things that we were talking. So let us see how the guidelines we will use here. So first is how much is the steady state error, how is it related to the loop gain, because now we are going to work with loop gain only. So the steady state error is related to the loop gain by assuming that what is the loop gain at s equal to 0. Okay, so basically this is the steady state error for a unit step input is nothing but limit. This comes from the final value theorem. Limit s going to 0, 1 by 1 plus ts, right? This you can find out. Okay, just putting a step input and see what is the error, and then that error you can put in terms of the loop gain. This expression will immediately come out. So for this, the limit s equal to 1 plus 1 by ts, and this will be 1 by 1 plus g into h at omega equal to 0. So for example, if the loop gain is 50 at DC, then the steady state error is approximately 0.02. Okay, so we should ideally have a very high gain at DC. In fact, if I put a PI compensator having a pole at origin, then the loop gain is very, very high. Okay, in fact ideally infinite at DC. Okay, how much is the settling time? The second question, how will we relate the settling time with the loop gain, right? So the settling time is related to the 0 dB crossover frequency of TS. Okay, suppose we plot TS and we find omega cross is the frequency at which the 0 dB is crossing for this loop gain, then roughly we can say approximately the settling time is approximately 4 by omega cross seconds. Okay, so this is how we relate the loop gain with the settling time. The third is what is the transient overshoot. Okay, this was the third requirement. Now that transient overshoot can be obtained by looking at the phase plot of the loop gain. Okay, so this is again coming from a textbook of control system. The damping ratio zeta and hence the transient overshoot is related to the phase margin by this expression phi m. okay, which is a little bit complicated expression, okay, but this can be seen from textbooks. And for a second order system, of course we are talking about second order system. So higher phase margin leads to lesser overshoot, okay, as you can, so we have actually plotted this equation, can be plotted here, okay, and you can see here that if the phase margin is like 30 degree, the overshoot is high, 37%. So it is a good idea to have like a phase margin in this region, okay, like 55, 60, or even this region, I will say 50 to 60 degree phase margin is a good thing, because then the overshoot is something like less than 10%. Okay, so this is a good approximation, right? And so here we see that there are three things that are important from the performance point of view, transient performance. These were number one, steady state error, and we have seen how the loop gain plot, from the loop gain plot we know how much is the steady state error. The second is what is the settling time, and we know from the omega cross of the loop gain what is the settling time. And the third is the transient overshoot, which we can obtain from the phase plot of the loop gain, right? So with these three understanding, let us now go back to the okay, that one more thing, that is we will start with this one. Yeah, so now what is the objective of the compensator? Okay, so when we introduce this compensator, we should make sure that the loop gain crosses the 0 dB line or the unity gain line with a slope of minus 20 dB per decade. So which means that when you plot it, so okay, this is your loop gain magnitude plot, close to 0 dB, okay, so this is the omega and this is the 0 dB. Close to this point, this should cross with a slope of minus 20 dB per decade. Okay, the why do we want to do that? Okay, near to this one, other places it can have minus 20, minus 40 like this, but when it is crossing at this point, it should be preferably crossing with a slope of minus 20 dB. Why is it so? Because this will ensure that the closed loop system is stable, because this resembles a single pole around the 0 dB line. Okay, and if you have a single pole around the 0 dB, what will happen is, as you can understand, what we are working with is okay, and so the denominator, right, the denominator, if it is one angle 180 degree, right, then it is going to have unstable, this denominator will become so at close to this omega cross, the gain is 1, but the phase, at the phase it should be far away from 180 degree, right? Otherwise the denominator becomes 1 minus 1, right? This denominator will become 1 minus 1, right? And then the gain, so the system will become unstable, right? So therefore when the loop gain is crossing, we should have a single pole behavior. So then if it behaves like a single pole, then what is the advantage is that with a single pole the plot is something like this. With a single pole, the plot is like this, okay, right? So you have a minus 90 degree fall in the phase, right? So therefore you will have a lot of phase margin. You are far away from the 180-degree line, minus 180-degree line, right? So if your loop gain is crossing the 0 dB with a slope of minus 20 dB, then you are safe from the phase margin point of view, right? So you have enough phase margin. Of course, you have, depending on the poles and zeros near the crossover frequency, you will not get exactly minus 90 degree. You may be like minus 120 degree or minus 130 degree, but you have enough margin, okay, from the minus 180 degree line, like 50-60 degrees, right? So that is what is a good thing, okay? So if you so we should try to make sure that the loop gain crosses the 0 dB line with a slope of minus 20 dB per decade. We'll see this one, okay? And if the plant is such that it already exhibits a single port behavior around the 0 dB line, then the compensator can be very simple, okay? It can be a gain with a pole at origin, K by S, right? Because if the plant itself is a single pole around 0 dB, then there is no stability issue at all, okay? And so it will become very easy for us to design, right? Now the compensator that we will use for the voltage source converter VSC is usually a PI compensator. Other types of compensators can also be used, but generally we have seen that the PI controllers can give a very good performance, okay, sufficient for our purpose. In some cases where there is single or double frequency, suppose 100 Hertz oscillation coming, then a PR controller can be also used. PR controllers work very well in a narrow band of frequency, okay? So so when you have 100 Hertz ripple, suppose you have a single phase system, you will have a 100 Hertz ripple on the voltage source converter, and there PR controller works sometimes better, okay? But for this kind of three-phase systems, we have seen that a PI compensator is good enough. So then you have this Kp plus Ki by S, and again I have written it in a normalized form, okay? In addition to the PI compensator, we can also add a lag lead compensator, okay? In this example we have not shown this, but you can always add a lag lead compensator so that you can manipulate the bandwidth, okay? You can shift the Bode plot up or down, or you can move it sideways, right? By adding these kind of lag lead compensators. This is useful in many other power electronic converters. For example, in DC-DC converters, sometimes we use a lag lead compensator in addition to a PI compensator. Sometimes we cancel some of the poles and zeros by this thing. But in this case, in this VSC example, a PI controller is sufficient, okay? So now let us put these values in the transfer function, okay? We have already got the values which I had shown at the per unit, and you put this GS and then you put like this, and then it comes something like this, okay, when you put the values. So the plant is a single pole system, and the pole is at R per unit by L per unit. So where is the pole? It will be at this point, okay, 0.0034 per unit, which is about 10.6 radians per second, okay? So the DC gain is 56.3 dB. What is omega cross? Omega cross will be at this point, okay, 657.1, 657 is here, 657.1 into 0.034. Again, this is minus 20 dB per decade. That's why I could write directly the multiplication, and this will become 22.3 per unit, okay? So we can plot it, right? So you can see here the Bode plot. This is 56 dB. Here it is this 56 dB, this one, and you will have omega cross here, okay, and this is 22.3 per unit, right? So this is 22.3 per unit, okay? This axis here, okay, this is incorrect, okay? This is not fully incorrect, this is radian per second in per unit. Okay, so this axis is in per unit. Okay, so I have plotted in MATLAB, and I could just plot it like this way only. So here you can see that, so therefore this value is 22.3 in per unit, and so but here you can see this is the pole, and the pole is at 0.034. so here you can see this pole is at 0.034 per unit. Okay, radian per second. Fine. So you can see here I have drawn the asymptotic Bode plot. Okay, so you can asymptotic phase plot, and the red one is the asymptotic gain plot, right? The actual plot is the blue one. The blue one is the actual plot. Okay, the asymptotic plot in many cases are very useful as a designer. Now, so once we have done this, we now add the PI compensator. Okay, and the PI compensator is something like this, a normalized form, and when you do that, the loop gain plot will become GCS into GCS, and it will come out to be an expression like this. Okay, so here you can see that these two factors, okay, this Kp, what it is doing, this Kp is basically controlling the gain, right? So what will it do? It will shift suppose you have a plot like this, it can shift this plot up or down depending on whether Kp is greater than 1 or Kp is less than 1, right? So you will be able to shift the plot. So for example, you can have a value of plot which is like this, or you can also have a plot which is like this. Okay, right? So what you can see here is that when you change this Kp thing, then the Kp value, then your bandwidth is changing. You see the bandwidth is changing, omega cross is changing, it is moving. So which means that this Kp value can control, okay, the crossover frequency of the loop gain, right? So this is something which we can keep in mind, that if you need a certain amount of bandwidth, if you want to make your system faster, you can control with this Kp thing. But if you put too much of bandwidth, then the switching frequency harmonics will come into the system. Also, we see here that there is a pole at origin. Okay, there is a pole at origin. So which means the steady state error will become 0, right? So this is one of the biggest advantages of a PI compensator. It has a pole at origin, and so the steady state error becomes 0, right? So this is how it will look like. So now one more thing that is important is the choice of the 0 placement. Okay, so here you can see there is a 0, this one. How to choose that 0? Okay, how to choose the 0? So for that there are two options actually. One option, so there is already a pole omega p, omega pole that is coming from the plant. Plant has a pole at a certain frequency omega p. Now the 0 can be placed to the left of omega p or to the right of omega p. You can see here the omega z is placed to the left, and here it is placed to the right of omega p. And in both the cases, the corresponding loop gain plot will change. So if I now suppose fix what is the omega cross, okay, so let us put this as omega cross as 40 per unit. So this will become 40. Okay, and why we have chosen this? Because as I told you, the switching frequency I want to be at least 10 times less than the switching frequency. The switching frequency is at 400 per unit. So I have chosen the omega cross of the loop gain TS. This is the TS plot. I have chosen it to be 40 per unit, right? much less than the switching frequency. So now you have two choices, as I was telling. The 0 can be placed like omega 0 less than omega p. For example, you can put it at 0.01 per unit, and here omega p is 0.034 and omega cos. But you can also choose the 0 to be on the right hand side of omega p. Now in this example, again this is where numerical values are important. In this example, what we see here is that if you put that omega z, okay, suppose you put a value of 0.01, this value, this is already 0.034, okay, right? Now here, if you put omega z less than omega p, suppose you choose 0.01, so this you choose 0.01 per unit, okay, this omega z, then you can see here that this this 0 is now getting very close to the pole at origin, okay, it is getting very close, it is 0.01 per unit, getting very close to the pole at origin, and then their effects will start to cancel each other, okay. The 0 close to the origin will try to nullify the effect of the pole at origin, and then the system response will become very sluggish, okay. So what we will do is we will not take this plot, okay, and we will not place the omega z less than omega p, rather we will go with this plot where omega z is more than omega p. And so so it is better if I choose omega z more than omega p. So let us take omega z equal to 100 times omega p, and which is 3.4 per unit. So now this was 0.034 per unit. I choose omega p equal to 3.4 per unit, and omega cross is 40 per unit. This is 40 per unit, okay. So therefore I have a pole at origin, so then this is coming, so there is a pole at origin, origin has a pole here, there is some pole, and then I have second pole coming here, okay, and therefore the second pole is making minus 40 dB, and then you have a 0 here, okay, which is making it again minus 20 dB, and then it goes ahead, okay. So now we have chosen omega z to be 3.4 per unit, and omega z is equal to ki by kp, and you can see it here in this expression, omega z equal to ki by kp. So ki by kp will be 3.4, right? And again I have told you that we want a bandwidth, the crossover frequency to be 40 per unit, so I want to adjust the value of kp, and therefore I will then, we have to do a little bit of, I took the example help of MATLAB a little bit, but I can also do it by hand calculation. Kp equal to 1.9 and ki equal to 6.46. So in this way the crossover frequency is 40 per unit, and I have a plot like this, which is kind of like a nice plot, okay. So I can plot it now here in this. Here you can see this is that 0.034, this is the 0.034, and here you have the 3.4, and then it crosses, so there is where it crosses, and this is roughly 10, 20, 30, okay, it is, yeah, roughly close to 40, okay, 10, 20, 30, 40, it is somewhere like that, 50 per unit, okay. And here actually the phase margin is quite high actually, but this is okay, this type of plot is not bad, okay. I could have actually shifted it a little bit downwards so that I could have got it the phase margin to be, yeah, I could have gotten something like here also. This was also a possibility, okay, with this value also, okay. This, in this plot, the phase margin is a slightly higher side, okay. But anyway, this is how we actually design the plot of the loop gain, and you can see that how we can actually get the values of Kp, Ki by looking into the Bode plot and adjusting the values, okay, so that we get what we desire. So there are three important, so summarizing, so there are three important parameters to look for: the steady state error, the transient overshoot, and the settling time, which are again related to the loop gain Ts. And if you analyze the Bode plot carefully for Ts, you can actually manipulate Ts by changing Kp, Ki parameters. You can make it up, down, you can shift it like that, and therefore you can satisfy all the three requirements as I mentioned by doing this Bode plot analysis. In the next section, in the next lecture, I will show you an example in MATLAB where we will do this. Okay, so thank you.